Alright, welcome back. So, last time we finished up doing our image views. So setting up the image structs and the image view structs, which were basically a view onto the images that we're going to render, which will then be presented to the screen. So then we got onto the graphics pipeline basics. And this chapter, this first section, I guess, of the chapter, goes through, turning the volume mood down a bit, goes through the various stages of the graphics pipeline. So it's input assembler, vertex shader, tessellation, geometry shader, rasterization, fragment shader, color blending. It's a few stages. This page just sort of explains what each one does a little bit, and then talks about some of the fact that these ones in green are like fixed, as in you can't really make any changes. If you want to change them, you have to basically destroy the whole pipeline and recreate another one, which may not be a huge deal, but that's what you have to do. Whereas ones in yellow or orange yellow, they are things you can actually send dynamic data to, which changes the outcome, I guess. So in the following chapters, as you can see by the names, we're looking at shaders, so probably the vertex and geometry and fragment shaders. And then the fixed functions will be like the input assembler, rasterization, and color blending, because the fixed you can't change them. And then render passes, but we haven't got to that yet. So I'm not going to go through all this. Feel free to do it in your own time. But just to mention again that these orange, they went for orange. They look yellowy. They are programmable. And the only bit of code to do in this section is to add a function called this. Create graphics pipeline within as the last function called so far in the init Vulkan function. So init Vulkan, let's go and create this call. It's probably going to take in our app pointer, and let's nip over here and add it in. So create image views, take me down there, and then just below here we'll create our function. Alright, well, thanks for joining me, that was really quick. I'm kidding. Okay, so on to the next, and just quickly save that and just double check everything's compiling. I haven't checked in a while. Build, come on, learn to spell. Yep, everything's up and running. We have no errors. Boom. Okay, so shader modules. First vertex, then fragment, then per vertex colors, and heaps of other stuff. Alright, unlike earlier APIs, shader code in Vulkan has to be specified in a bytecode format, as opposed to human readable syntax like GLSL and HLSL. The bytecode format is called SPRV, and is designed to be used with both Vulkan and OpenCL, both Chronos APIs. It is a format that can be used to write graphics and compute shaders, but we will focus on shaders used in Vulkan's graphics pipelines in this tutorial. The advantages of using bytecode format is that the compiler is written by GPU vendors to turn shader code into native code and significantly less complex. Okay, well, yeah, it probably will be because they're lower level. The past has shown that with human readable syntax GLSL, and some GPU vendors were rather flexible with their interpretation of the standard. If you happen to write non-trivial shaders with the GPU from one of these vendors, then you risk other vendors' drivers rejecting your code due to syntax. So if you're a little bit more specific, it would be a lot less, or a bit less, cross-platform. Okay, cool. So they use these compiled versions as bytecode to make it a bit easier. However, that does not mean that we need to write this bytecode by hand. Hopefully not. Chronos has provided their own vendor-independent compiler that compiles GLSL to SPRV. This compiler is designed to verify that the shader code is fully standard compliant and produces the SPRV binary that you can ship with your program. You can also include this compiler as a library to produce SPRV at runtime, but we won't be doing that in this tutorial. Ooh, you could do like a lot more dynamic shaders. Interesting. Although we can use this compiler directly via glsl lang validata.exe, we'll be using glslc by Google instead. The advantage of glslc is that it uses the same parameter format as well-known compilers like GCC and Clang, and includes some extra functionality like includes. Both of them are already included in the Vulkan SDK. Fantastic! So you don't need to do any download or anything like that. Awesome! GLSL is a shader language with a C-like syntax, performs written, blah, blah, blah. Okay, I'm not going to go into the ins and outs of GLSL. Vertex shader. The vertex shader processes each incoming vertex. It takes its attributes like world position, color, normal, and texture coordinates as input. The output is the final position in clip coordinates, and the attributes that need to be passed to the fragment shader, like the color, texture coordinates. These values will then be interpolated over the fragment by the rasterizer to produce a smooth gradient. A clip coordinate is a four-dimensional vector from the vertex shader that is subsequently turned into a normalized device coordinate by dividing the whole vector by its last component. These normalized device coordinates are homogeneous coordinates that map the frame buffers to a -1 to 1 by a -1 to 1 coordinate system that looks like the following. Okay, so this is the actual sort of image size, you can say, or it says there, frame buffer, and this is what it gets turned into, normalized to. All right, awesome. You should already be familiar with these if you have dabbled in computer graphics before. Yes, if you have used OpenGL before, no. Then you'll notice that the sign of the Y coordinates is flipped. The Z coordinates now uses the same range as it does in Direct 3D from 0 to 1. Oh, interesting. Okay, cool. There's a little triangle. Our first triangle, we won't be applying any transformations. We'll just simply specify the position and the three vertices directly as normal device coordinates to create the following shape. We can directly output normalized device coordinates by outputting them as clip coordinates from the vertex shader with the last component set to 1. So that'll be what it's divided by. Yeah, okay. That way the division is to transform clip coordinates to normalize the device coordinates will not change anything. Normally these coordinates will be stored in a vertex buffer, but creating a vertex buffer in Vulkan and filling it with data is non-trivial, like a lot of things in Vulkan. Therefore, I've decided to postpone this until after we've learned a few more things, so we're no longer the new kids in the block. Okay, so let's create this vertex shader. Or this is a vertex shader. The main function is invoked for every vertex. The built-in GL vertex index variable contains the index of the current vertex. Okay, so if it was like index 0, 1, 2, as it cycles through. Oh, excuse me. The position of each vertex is accessed, and the constant array in the shader is combined with dummy Z and W components to produce a position in clip coordinates. The built-in variable GL position. Did I just skip ahead? No. Functions are output. Okay, so this here. Okay. Alright. Fragment shader. Triangle that is formed by the positions from the vertex shader fills an area on the screen with fragments. The fragment shader is invoked on these fragments to produce a color and depth for the frame buffer or frame buffers. A simple fragment shader that outputs the color red for the entire triangle would look like this. So this layout location equals 0. This is the output. It's a 4 vector 4 output color, and here it is. So you define it outside, outside of the main, and then you can access it just like global variables, I suppose. And you set that output. Okay. The main function is called for every fragment, just like the vertex shader main. Function is called for every vertex, but okay. Colors in GLSL are 4 component vectors with an RGB and an alpha channel with a 0 to 1 range, unlike GL position in the vertex shader. Let's just remind ourselves about that. this thing here. Wait, this thing here, sorry. Yeah, okay. The vertex shader, there is no inbuilt variable to output a color for the current fragment. You have to specify your own output variable for each frame buffer where the layout equals location 0. Modifier specifies the index of the frame buffer. Okay. Is that like a default argument then, I guess? The color red is written to this output color variable, and that is linked to the first and only frame buffer at index 0. Ah, okay. Because you've only got one frame buffer. You only got one. Per vertex colors. Making the entire triangle red is not very interesting. Wouldn't something like the following be a lot nicer? Yes, it would. So, okay. So we have to, we're making a map. Alright, so based on the index, we are picking a specific vector 3 in our vertex shader. And then when it comes down through to the fragment shader, it picks the right color. Okay. Alrighty. Yeah, like that. Okay, excellent. The input variable does not necessarily have to be the same as the name. They will be linked together using the indexes specified by the location directives. The main function, blah, 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 blah. Ignore all that. Compile the shaders. Create a directory called shaders. Yes, ma'am. Okay, shaders. In the directory, okay. And then in there, store a file shaded.virt. Okay. Touch. I'll do Emacs. Shaders, shader.virt. In there will be all of this JS, which I'm just going to copy because I'm not going to write that out manually. Right, so that has our location, our output vector called frag color. So this is the vertex shader, and it's going to have an output called frag color, which we're defining here. Okay. And the content of shader.frag should be this. Shader.frag. Huh. Whoops. Helps if you copy that thing first. Oh man, why do you want to do that? Okay. Cool, so we have our vertex shader and our fragment shader. We're now going to compile them with SPIR-V bytecode using GLSLC program, which should come in our Vulkan SDK. So let's kill these. Where is which GLSLC? Okay, that's where we are. So we need to pop that into something like this. Pause. Okay, so create a compile.bat file. Nope, I'm not using pause. Create a compile.sh file because we're on Linux. And do this kind of thing. All right, let's create that. But first, let's copy this because we're going to need that. What was it? Compile.sh. That is the location of GLSL, and then we say shader.virt. It already knows it. Output as virt.spv. Output as virt.spv. Just SPV. Okay, and the second one is just shader.frag. The output is frag.spv. Excellent. Now I need to chmod that. So chmod plus x compile.sh. End of program, platform specific code. Okay, these two commands tell the compiler to read the GLSL. Yeah, it seems pretty self-explanatory. Compile this to this. And it checks for syntax errors. That's cool. Compiling shaders in the command line is one of the most straightforward options. and it's the one that we'll be using in this tutorial. But it is also possible to compile shaders directly from your own code. The Vulkan SDK includes libshaders.c, which is a library to compile GLSL code to SPRV from within your program. Okay, loading the shader. Oh, let's actually compile it first. Compile. Error, linking model files is not supported yet. Hey? What? Linking multiple files. Oh, you gotta put output. That's likely what the problem is. It is what the problem is, so let's yay! Woo, look at that. Got our little, where's the hell's that compiled stuff? Oh, we compiled it to here. Alright, let's just remove frag and shader dot, no wait, vid, sorry. And let's edit this to actually put it in shaders. Try that one more time with feeling. Then list out here, it's not in here, so let's list out that. There you go. There's our SPRV and SPV files. Okay, cool. So at least we know that the compiling works. Now back to the code. Now we need to load our functions, load our vertex and fragment shaders. But let's, okay. Oh yeah, we need to load them into the program and plug them into the graphics pipeline at some point. We'll first write a simple help function to load the binary data to things. Okay, so file opening and reading in C. This should be fun. Okay, so we've already got, well, fstream, we don't need that. We've got standard IO. So we want to create a new static function by the looks of it. Now, I was watching Handmade Hero the other day. It's like an old man telling a story. And Casey was talking about how back in the day, using static on various things, but like functions specifically in this case, helps the compiler to know that those particular functions and stuff aren't being used anywhere else and are never going to be accessed outside of the particular file. So it made some performance in compiler and maybe even the running of the program made some kind of performance in those areas back in the day. Not sure if it does anymore. I have not been using static at all in this set of videos, so I'm not going to do it now. But I might do it later to see how that actually performs, because that would be pretty cool. Yeah, I might add that. But for now, let's not do that, because everything's all in one file anyway. We haven't done any abstractions. So we are returning from this file, from this function, an array of characters, because it's going to be a binary file. So let's do char star, and the function is called read file, taking in a const star char star of file name. And what else is it going to do? So it creates if stream file. Oh, so file must be C++'s way of opening a file. So this is like an error check. So we could do that. If fopen fails, and fopen takes the file name and the access type, I believe. So file name, and the access type is going to be, we're reading a binary if my memory is correct. So if that equals null, I think that's the error. Then we'll say exit with number 7, or what number are we up to? Looks like we're up to number 7. Actually, we've got number 6. Yes, we're doing that. And we're going to print F to say failed to open. Oh, let's give it the name as well. File name. Yeah, okay. Otherwise, we'll carry on with our lives. If file dot is open. Oh, I don't know. If maybe we can do that in C. Probably can. We can do it in C++. You can definitely do it in C. Yeah. But I know what we do need to do is create a file pointer to file. Is that what it's called? It's all capitals, isn't it? Yeah. Which we're going to then use to get the data out. I mean, we're going to use the pointer to the file. So I think we have to do like, when we do fread, before that we need to do an fseek to the end. And then from the end we can find the length based on we move the cursor to the end of the file when we're reading it with fseek. And we can find the size of the file from that, I think. In fact, let's Google that. C language, open, binary file. Read and write binary files. I've already looked at this before. Oh, Stack Overflow. I really want that. I want to see someone. Oh. Yes. Yep, we're creating a file pointer. We specify the read operation. Any write operations. Oh, okay, fine. Seek moves the pointer. I thought I said it was cursor to the requested record. Keep in mind that C thinks of everything in the disk file as blocks of bytes read from disk into memory or read from memory onto disk. Read from memory disk using the file pointer. Okay, so that's the file pointer is our cursor essentially then. So what's this rec? Don't know. We've got a file pointer. They're storing everything in some sort of struct called rec. There's fopen, file name, write access. If that is null, yeah, you've done that. Then loop through. What's 10? What's that magic number all about? Oh, it reads and writes 10 arbitrary records. Oh, I want to know. C language. What do you want to know? Get size of binary file. Hello. Cool. Geeks. 4 geeks. I've already looked at that too. What have we got? fseek and ftell. Ooh. The idea is to use fseek in C and ftell in C. Using fseek, we move the file pointer to the end. Then using ftell, we find its position, which is actually the size in bytes. Because it's binary, we know that's absolutely correct. Excellent. Okay, so we can actually, once we've opened the file, we need to fseek to the end of the file. We actually need to specify this further up, and this becomes our. I can't do that, can you? Fopen becomes our. Yeah, okay, let's do it this way then. That equals fopen, and then we can say. Then we can do the check to see if fopen is null or not. Not fopen, sorry. Our pointer. If it's a null pointer, as in this did not work, then we know there's a problem. And then we can use fseek, passing in our file pointer and the 0, and I think it's L for long, as in long int, and then seek end. Cool. And then we will call our ftell, passing in the file pointer again, and that would give us the size of, let's just go long int. Well, size t, because I'm not entirely sure that's right, but let's just call it size. So we've got a size, and I want to print that out, and then we can verify it. File name size equals size, and we're going to pass it our file name and size. Then as we, why are you complaining? D expected to be int, but it was a size t. How do you do? Is it itself a long? It is. Size t is actually a long anyway. Okay, cool. Then we should always remember to fclose our file pointer. And then return. Let's just return that for now. FL close. That's better. Okay, so we've got our size. We've got the pointer to the file, so we can play with that. We also could go back to the beginning to do that read. So we'll probably do, fc like back to the beginning. Yeah, I think that's called. What is it called? Seek end, seek set, I think. Come on, seek end and seek set. Get in. I remember something. Yeah. Okay. So we are opening the file, quick bit of error checking, seeking to the end of it, getting the size using ftel, and then seek back to the beginning, because eventually we're going to want to read. In fact, let's just do that now. For u32, I equals 0. I's got to be less than size I plus plus. I think we're going to get a problem here, aren't we? No, we're not. It's fine. Okay. Print out whatever is in this file. This byte, basically. Don't want to do a new line, but I will here. Let's say something like end of file. New line again. Right, we're going to print out something. Are we going to, is it like print out the file pointer position? Like that, I wonder. At position I? How do you print out binary? It's not going to be a string, is it? Like a character? No. Escapate the child star, but we have type file. C print printf binary. Binary format specifier. Come on. Include help. What's that? Studytonight.com. I don't know what the website is. It's weird. Let's just do Stack Overflow. Hopefully you can help me out. I bet it's just a B. Oh, is it a B? No. Well, it's gonna be a number in it. So long? No. Damn. What are you? Is there a binary format? Binary representation of a given number? Code grepper. Help me out. D. That's C++, my friend. No, it's not. He's using bit shifting. Why are you complaining? What if I put, if D doesn't work because What are you overlaying here? Format d expects a type int. The argument is file. Okay, maybe we have to search for the following thing. Format printf file byte. Maybe it's that. That's saying dot thingy b. Oh, I'm spending way too long on this. I'm just gonna ignore it in a second. Yep, scratch that. Print nothing. Alright, let's just run it, see what happens. Alright, what do we get? Nothing, because you didn't call the function. That'll be the reason why. Let's just call it here. And we are going to pass in a string to our file. So shaders, what was it? Vert.spv. I think. Yep. Nope. Didn't get any errors, but oh, we're not calling this. Yeah, we are. Calling it here. And then we're calling read file, which is right there. Why did that do nothing? Ah, we're returning nothing. We're not printing anything else. It's printing the size of them there. And back we go. Yep, okay, so get rid of this chunk of code that I didn't want. Keep that other print. There you go. Now print me out something beautiful, please. Vertex is of size 1504, so we can do ls la shaders 1504. It's accurate. Okay, that's good. We know that the byte size is correct when we are reading the file. That's good news. Over here, we may as well call frag. Actually, let's also call a fake one. Buff. Build. Fail to open shader buff.spv. Excellent. We know that works. Oops. Okay. Ignore you, and I'll come back to that stuff later. Okay, so we're getting this far. The file read function will read all of the bytes from the specified file and return them in a byte array managed by this vector thing. Yep, we already did that. Oh, file size, we've done that too. Telg, could have probably worked it out. That was ftel. Stores it in this buffer. Is buffer a function? Allocate a buffer. After that, we can seek back to the beginning of the file. Yeah, we did all that too. We're not allocating it to a buffer though, but we totally could. How do we do that then? Have to be a char array. Let's just call it buffer. So at every, what do we need to do? We need to pass the contents of the file pointer's data into our buffer. With fread. I think we can do that with fread, can we? Yeah. C language fread. The C library, blah, blah, blah. Yep, so the file pointer, the size that we want to read, the size, I don't know what the hell that is, and then the file stream. Reads data from the given stream into the array. Oh, okay, so that's the data I'm putting in initially in the first argument. What's this n member? This is the number of elements, each one with the size of size bytes. Oh, we're just using char, which is only one, so 1 byte. Okay, so once we've done, we've got the correct size, so we know how big it is, the file in bytes. Then we'll do fread, and we'll pass in our buffer and the size, and this is 1. So we could, I mean, to be super duper safe, we could do something like size of char, and also the actual file. So p file, hey, p fiolie with it. Cool. What's the error here? Buffer may be used uninitialized. That is true. Oh, that is true. Let's create it down here with a size as its initialization. And because we know how big it is. Excellent. And then that's what we're going to return. But first, no, that's what we're going to return. We're returning a local. Cool, there you go. I think that's right, isn't it? Yeah. So these will be char star of vert. Let's find out what we're going to call them actually. Vert shader code, that makes sense. Vert shader code equal to that. And here will be char star frag shader code. Alright. That seems pretty reasonable, I think. So we're returning a buffer. We'll now call this function from, yep, and we did that. We haven't got this auto, but we know what's coming back. Make sure that the shaders are loaded correctly by printing the size of the buffer and checking for any match in the actual file size. We did that already. Excellent. Creating shader modules now. Before we can pass the code to the pipeline, we have to wrap it in a VK shader module applet. Let's create a helper function called create shader module to do just that. Oh, I'm so excited to do that. VK shader module takes in a const of something, const star char, or char star even, sorry. And that we're just going to call it code, or codo, if you like. This function will take a buffer with the bytecode as a parameter and create a VK shader module from it. Yeah, we just said that. Creating a shader module is simple. We only need to specify the pointer to the buffer with the bytecode and the length of it. Oh, and the length of it. We don't have the length of it. This information is specified by the VK shader module create infrastructure. Let's take a quick look at that potentially. The one catch is that the size of the bytecode is specified in bytes, but the bytecode pointer is a uint32. The pointer, so we need to pass uint32, so we need to cast it rather than chars. Okay. Therefore, we will need to cast the pointer with, I think, just a regular cast rather than that, as shown in the code below. When you perform the cast like this, you also need to ensure that the data satisfies the alignment requirement of uint32. Luckily for us, the data is stored in std vector, where the value allocator already ensures that the data specifies the worst case alignment requirements. Now, I don't remember from reading through Effective-C what that alignment stuff means. It was only like a month ago, but I have already forgotten. I'm just gonna do it and hope for the best. Hopefully it actually errors out if there are any problems pretty early on and we don't have to deal with weird insidious bugs later on. Oops. Okay, back to our fun time of creating structs of stuff. We don't need the data, we just need the code, and we don't do that either. we're just going to cast it to a U32. And it's not going to be a const. Excellent. Oh, we need to have that opening parentheses, curly brace. That size. Now then, our code is just an array of chars. I don't know if we're going to be able to do that. What's that problem? Cast from pointer to integer. Oh, yes, can be it. That. Ooh, we haven't got our size. I suppose we could return it from. Well, we're going to be doing this, aren't we? With our. There's a shader module and probably this other shader too. But could we return? There's no multiple returns in C, so we can't return the code, like the buffer from here, and the size of the buffer. What we could potentially do is create some kind of struct to do that thing. Yeah, okay. Struct, and let's call it something like file, shader file. Okay, and it's going to be called shader file. Okay, it has code on it and it has size t, size, and code is char star code. What a bummer that we've got to do this, but let's just do it anyway. So we're actually going to be accepting our shader file, and that's going to be shader file dot code. Oh wait, oops, size. Shader file dot code there. Oh, or some of the shader. Okay, fantastic. So now our read file is actually going to return a shader file. So this is going to be a shader file. All right, but now we actually need to return a shader file. Sorry. Let's call shader is this thing, and we have the size equal to the size, and the code is equal to our buffer. Whoops. Yep. Okay. Why are you not happy? Why are you not happy? Code undeclared. Yeah, this is a shader. Just created you right here. What are you saying? I don't know what your problem is. Missing initializer. Field code shader file. What do you want, the address of that? That's interesting. Each undeclared. Creating a new struct of type shader, and it's equal to this. Oh, you tool. And that does indeed have to be that. Okay, that's nice. So we get our shader files, pass them into these, and then comes out here, and so far not really any errors. So that's good news. Moving on. The VK shader module has then been created with the call to the VK shader module. Okay, let's just copy that and C++ it. Creating our shader module. Oh, here we also need to now pass in our app, because we need the device and some other stuff. So let's go down to here and pass in to these functions our app. Cool. Okay. And exit out because we failed to do something. We got exit 7 already, so let's exit 8. Although we're in the same path, exit 7 it is. And this is going to be our P app. Whoops. Device. Yep. And our create info. And our shader module, which we just created here to populate. Alright, excellent. Why are you not in the right place? Okay. These parameters of the shader are those previous objects, creation functions, blah, 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 blah. Okay. The buffer with the code may be freed immediately after creating the shader. Oh, don't forget to return the created shader module. Okay. The parameters are the same as those in the previous object creation functions. The logical device pointer, the create info, optional pointer to custom allocators, and the handle output variables. The buffer with the code can be freed immediately after creating the shader. Well, we're not storing it on the heap. So really, this is where it's stored initially. Okay. Okay, the shader modules are just a thin wrapper around the shader bytecode that we previously loaded from the files. Blah blah blah. Okay. That means that they're allowed to be destroyed. The shader. Oh, okay. So we can destroy them like right after we've done these function calls. Really excellent. So at the bottom, boom. So this doesn't need to go in the cleanup. P app. Here's our device. These need to return vid. And the type that we're returning is. Here you go. And this one is called. That's the wrong one. Frag. Excellent. So we're doing that cleanup, and then we're doing this cleanup right here. Wunderbar. Let's just give that a compile, see how it wants to play. It doesn't want to play. Seg fault. Getting a warning about fread, because fread has output, and we don't really care about the output. Seg fault. So what happens if I comment this out? Seg fault again. Where are we seg faulting? Let's just get rid of all this. So that runs. But as soon as we start to play with these, it doesn't want to run. It doesn't like something. It doesn't like these. Let's have a look at inside here. What have you got here? Print F. Let's look at our. Actually, it's called the shader file size. Should be a integer, I believe. Size. What's wrong with this? You are indeed a struct. Why are you not playing? Oh, we're passing a copy of the struct. Ah, maybe we need to. Yes. We need to pass the memory address of that struct. So in here, we know it's the memory that we're playing with. So that would allow us to actually use that locally scoped variable outside of its function, because this function is being called from within that function. Oh, we still say fault. We have a size though. Oh, we have an error with the size. What's that say? For what do you expect? It's a size T, so it should be DL or LD. Sorry. That's interesting. Maybe because I don't know. Maybe why. Let's do something else. Let's say if shader file code equals null, then let's print is null, just to see what's coming out the other end. Well, it isn't null, so we know that much. But I wonder if it's what we expect it to be. Let's just print out the first item. The first byte of it. It should be binary format, so we should be able to do this. Shader file code at position 0. Oh, it doesn't even want to do that. What if we move that to the top before anything's accessed? No. Oh, that's causing the error. Is that causing? That is also going to cause the error. Yeah, okay. We obviously haven't got the memory or the data that we think we have. All right, so that's a problem. So I think the problem is likely going to be in our call to everread, we need to actually be passing some memory addresses around. So if we can create this struct, let's try this. Let's create a struct. Let's just 0 initialize it. So at least it's somewhere in this stack. Let's call it vert shader and frag shader. Pass that in to this function to be used, the memory address of that particular thing. So we say, here's a memory address of our local stack vert shader and frag shader, just shader in general. Use it and put your data into that, please. So a pointer to shader memory. Then you don't need to create your own one. We actually just say shader size equals this size, and then shader.code should equal that code. And then we just don't return anything. We don't need to. We've already updated that code locally, so we can probably remove this return statement. It'll be a void. And why are you complaining? Oh, because we don't care about this. In fact, that's a good point. We don't care about these, but we should rename this to this. So we keep using the same thing. All right. Now are you satisfied? No, you're not, because you got the wrong names. There you go. Now that one's satisfied. Are you going to be satisfied? Yes. Let's try running that again. Bugger. My theory was crap. We did possibly update the memory address, but that's it. Okay. In that case, I have a last ditch attempt to get this to work. And it's gonna be, let's just create some, oh, why does that not work? I was gonna say, let's use malloc and allocate it on the heap so we know for sure it's gonna be there. So we can pass in our vertex shader pointers, our shader pointers to here. And then as we go through, use this size to actually update the struct, and then I think I know what it is. I think I might know what it is. I don't know why I did that, sorry. The code item in the struct is what we need to remain, what we need to be on this, on the heap, I think. Not necessarily the size, just the code. I think. So let's, God, I'm an amateur at C. Let's keep these, oops. Yeah, let's keep these two shaders and pass the addresses to our file read. Out of consistency, I think I'd like to do this just real quick. Yeah, so what we're actually going to do is shader size is going to be equal to that response from ftel. Probably could do some error checking there as well. fseek is the one that not fseek, sorry. Oh, what's this error all about? Oh, sorry, shader size. Now this bit here is the bit which I think we need to change to be shader file code. Yeah, shader code is equal to, and we're going to cast it as char star, excuse me, and malloc this size of char multiplied by size. So that'll give us the space we need available within this struct code, and because we're getting a pointer to it, it should actually allocate that specific code on the heap, just the code or the code memory addresses on the heap, and then we pass that into this fread function, and fread does need like a size t response for like read count or something, and we could do what's that size t, we could do a check here to say something like if read count doesn't equal size, because we know there's bytes, and we print out we are missing some bytes, and then just for the hell of it do that just so we can see what's happening. Size t, no, okay, u32, why not? You don't return a u32, do you? You definitely return a size t, which is a long. What are you not liking? Implicit declaration of function read. Oh, because it's fread, isn't it? There you go. What if I make you u32? It's fine. I can also compare this, they're both the same, the size t's, so whatevs. Alright, and then we actually don't need to do any of this, that's fine. Then we make sure that we close. Why are you complaining about that? What are you saying to me? Size must be used. Oh, right. Sorry, it's shader size. And there's shader size 2. Oh, shader size. And you're going to be saying, you're trying to compare two different things, yo. Size maybe, oh god, no you're not. Shader size. Right, is that enough? Everyone fine now? Get rid of that. Right, we're all happy. Okay, now let's try that. We're missing some bytes. Why is that? I didn't think we were going to miss bytes. Okay, we get this because we're not freeing that, I think. But let's come. Oh, We might stop getting it if we do this. But let's do some comparisons. Printf red this many, which I think is going to be a long. It should be this many. And let's give it the read count and the shader size. So then we can figure out exactly how much we're missing, if anything. Red 1 should be... oh, read count is not what I thought it was. It's the number of times it pulled out the bytes it required. So like if you had a file stream on a really large file, the read count would probably be more than 1. Oh, don't quit that, but quit this. And we didn't get the warnings like we did last time because we are doing our cleanup. That's good news. All right. How do I not care about the read count? Let's print read count for absolutely no reason. I really want to do that, but it's going to shut up my compiler whinging, so. What are you unhappy about? Pull my LD. Oh, I've got to pass in the read count. That'll do it. Okay, so we've got down to here. This has already been quite a long one, so I think this could be a good place to stop. And then next time we'll jump onto the shader stage creation. That's good. Let me just do a bit of cleanup. Yeah, I think that's actually kind of clean enough. Is there any more? No, we're particularly logging out anything fancy. All right, excellent. Let's just do a git status. Oh, probably want to omit our compile. No, do we? It's just small binaries for now. We can probably omit them later from git add all of my things, git commit. What did we actually do? We created shader modules. Did quite a bit actually. Created shaders, loaded them, and created modules. Right, git push origin main. Excellent. That's it for now. I'll catch you next time. See ya.